Reijo is from US. I think you are in the US right now, isn't it?
Yeah.
Okay.
Yes,
He's from Berkeley. He's a researcher at the Berkeley National Laboratory. And Reijo was one of the, key collaborator inside Planck. And he will tell about NPIPE. This is a different way to analyze the data that's been performed just after the last release. Please, Reijo, go on.
Thank you. My name is Reijo Keskitalo, and I'm going to describe the Planck data processing pipeline called NPIPE, and really representing a collaborative effort of several tens of individuals. Can you verify that you're seeing the slide 2 of my slide deck?
Yeah, absolutely. We can see.
Good, excellent. So first of all, what is NPIPE? It's a data processing pipeline built on the Toast time order data processing framework. Toast itself is a package of open software that you can find on GitHub, and it allows for efficient time order data processing of data and also simulation. NPIPE is a collaborative effort, as I mentioned, combines 2 decades of software analysis techniques and expertise developed on Planck for both of the Planck instruments. And it's built to run on any supercomputer, or it'll even run on your home computer if you have enough disk space to store the time ordered data. The system that we have run most of our simulations is the NERSC flagship machine called Cori, with about 9,600 cores on 9,600 compute nodes and a whole ton of flops, which really allows us to dig into the noise and run a ton of simulations to back up with the real data processing. The pipeline itself processes raw time order data signal into frequency maps. And when I say raw, this is really the ADU value digitized signal with minimal pre-processing when it's loaded into memory and when the processing starts. And all of that is exposed in the pipeline and in the released software. You can look into how those bits are transformed into calibrated time ordered signal and how those signal are projected into frequency maps. NPIPE is the first pipeline to handle both Planck LFI and HFI data in a common framework. Hopefully not the last. Some of the things that make NPIPE special among other Planck releases and Planck processing pipelines. I've highlighted here 3 key differences that we have collected from the individual that we thought made the biggest impact and the biggest difference in the data processing. And probably right at the top of the list should be mentioned the use of multi-frequency information to build these polarization templates to break degeneracies that otherwise severely compromise the large-scale polarization and the calibration of Planck data. And another key feature of the pipeline is this global fit approach, where you fit for the gain fluctuations that you try to calibrate your instrument, but you're also correcting for bandpass mismatch and many other effects that we'll go into detail in just a few slides. So this global fit approach and the use of multi-frequency data to break calibration degeneracies are probably the 2 key pieces, along with the use of the generalized Destriper, which was already mentioned before, extending the use of that Destriper to HFI data, using the same Destriper and the same very short baseline length to process the entire data set, allows us to tackle especially the intermediate scale uncertainty in Planck. Here's a visualization of the power spectrum of a D-striped map as a function of the length of the baseline step that we're fitting. And instead of a simulation, the HFI instrument carried to dark bolometers that weren't exposed to optical signals. So we had genuine instrument data that we could destripe into maps without any signal cleaning to expose just how much of the noise we were able to subtract. And if you follow these baseline lengths on this curve, you see a suppression of power, especially at these degree angular scales, as you would naturally expect as you add degrees of freedom into your signal model. But there's also another feature that is worth mentioning, that at the largest angular scales on the map, you don't see the same improvement from shortening those baselines and adding these degrees of freedom. And that's because these scales are driven by the irreducible uncertainties left by the Planck scan strategy and the level of 1 meter of noise, correlated noise fluctuations in the data. Both very relevant features in the Planck data. I have here 2 more slides of comparing differences between the NPIPE processing and the 2018 public release 3 of Planck data. And this is not to highlight how NPIPE is somehow superior or better or anything like that, but the way we've come to describe Planck data sets has been as a delta of the earlier Planck releases. Otherwise, I would have to describe a whole lot more stuff than we have time for. So I'll focus on the differences in the processing, things that NPIPE does differently than in the 2018 release were done. And hopefully this allows a more concise treatment of NPIPE as a whole. First of all, we in the NPIPE processing include the 4-minute repointing maneuvers between each stable science scan period, each observation ring, and we also include the incomplete survey 9, and all of this amounts to about an extra 10% of integration time that goes direct into suppressing the small scale white noise in the NPIPE maps. We've also improved on the pointing model since the 2018 release. Most importantly, there are certain sub-arc minute systematic corrections that follow from improvements in the catalog on board the spacecraft. Planck was really fortunate to have a sister spacecraft, Herschel, that launched at the same time and used the same star tracker technology. So that high resolution instrument provided pointing model corrections that could then be applied to Planck that didn't have the same sensitivity to small angular scales. Now there's a pretty novel thing in the sky load differencing in the Planck LFI signal. Mark already discussed this at some length, so I won't go into too much detail, but it really is phenomenal how the radiometers and the amplifiers produce these significant 1/f noise fluctuations in the time ordered data that essentially make the entire data vector look like one long fluctuation, and the signal itself is very difficult to see. But when you have this reference load and the sky signal being looked at the same time, the difference between those two signals cancels most of those correlated noise fluctuations and leaves you with the scientific signal and the white noise. And we looked at this differencing tool in the pipeline, and we realized that this differencing, while it was really effective in suppressing the low frequency noise fluctuations in the data, it was also injecting a certain amount of white noise from the reference load signal into your science signal, which was obviously undesirable. So we came up with this optimization scheme where you not only optimize the coad weight of the load and the sky signal, but you also optimize over a low pass filter that suppresses the white noise in your load signal so that it doesn't get injected into your sky signal and into your science analysis. And the results are shown in this bottom plot here, where we plot the power spectrum of the difference time stream. And with these additional degrees of freedom, the the pipeline is able to optimize both the low frequency noise content of the signal and the high frequency noise content of the signal without making any undue compromises. And this shows up then as an improvement in the small scale high frequency noise in the NPIPE maps. Furthermore, we've tweaked the HFI cosmic ray glitch removal, which has a notable impact because there is a glitch, a cosmic ray glitch in every second of every detector data on HFI. So even small tweaks and small improvements in that process can yield great returns. We've also revisited the treatment of the 1 Hertz housekeeping spikes in LFI and the 4 Kelvin cooler interference, both handled via harmonic template fitting and correction in the NPIPE pre-processing. Other differences that really will stand out are, for example, the fact that we do not subtract the solar system dipole from our time ordered data during the processing. So if you just go about loading NPIPE maps and the PR3 2018 maps and try to run the same code on both, you're going to get hit by this fact that the solar system dipole is left in the maps. The reason why we chose to do this is that solar system dipole is the best indicator of the robustness of your overall absolute calibration. And if you're doing any cross-spectral analysis between these maps, you need to know that. And especially if you're trying to do any multi-frequency analysis of the temperature data, you need to be aware of there being a small calibration error left in the pipeline. So, good thing to keep in mind. We've also revisited the way the detector splits or data splits are defined. In the past, there have been half ring splits, odd even ring splits, half mission splits, and survey splits. And we looked at all those splits and decided that they weren't optimally independent because many of the systematics that affect a certain half of the data will also be there in the other half. So any cross-spectral analysis will be automatically biased by at a very low level, but arguably still there, if you treat these splits as independent while they're not. We have, as a very low-hanging fruit, we've increased the number of transfer function harmonics in HFI processing, which actually has a very clear impact at the 353 gigahertz processing. And we've also implemented an interpolation scheme where some of the systematics templates are sampled into exact sample positions rather than pulling values off a low resolution Hilpix map. And for such a trivial improvement, it is remarkable what that does to the galactic center. Here on the right, you have plots of the polarization amplitude of the Planck 2015, 2018, and the NPIPE maps at certain HFI frequencies. And these diagonal stripes that you see, or these pixelized shapes that you see in the 2018 maps, come from a low resolution carbon monoxide template that in the NPIPE analysis interpolated into the exact source positions or sample positions and avoids these artifacts. And as you can guess, it does have a measurable impact on, say, the power spectrum. Also, some of the things that we released that aren't available in the earlier data sets are the single detector and the single horn depolarized maps that can be used for temperature analysis of the data. And as a bonus, the high frequency single detector maps have been binned at a higher end side, higher resolution, to take advantage of the narrower beam and to fully sample the beam. And finally, we ran a campaign of measuring and improving on the ground measured HFI polarization angles and efficiencies, and found some corrections that were bigger than had been anticipated during the ground calibration campaign. This improved detector agreement and then allowed us to do better on other systematic template fittings. Here is a busy slide about what exactly the NPIPE formalism is. While the slide is busy, the formalism itself is not. It's all encompassed here in this very simple formula, where a vector of all the detector samples accumulated by Planck is a sum of some stationary sky signal unrolled into time domain by a Poynting matrix and a template matrix, time domain template matrix, which in typical Destriper or classical Destriper formalism is just a set of baseline offsets in each column describing how the detector noise level travels as time goes by. But in the extended Destriper formalism, first championed in the HFI analysis, the definition of this time domain template matrix was extended to include gain fluctuations, carbon monoxide templates, and other bandpass mismatch templates, and transfer function residuals from the bolometric transfer function deconvolution. And these templates are unrolled into time domain by a vector of template amplitudes here. And what's left in the data model is some simple noise vector. The only uncertainties in this data model are the pixel values of the sky that you're trying to solve and the template amplitudes that you're trying to fit for. And if you were really aggressive, these two linear descriptions could easily be collapsed into a single linear description, and you would essentially be solving a generalized least squares problem subject to whatever noise covariance you assume on n. So the formalism is not difficult. What you exactly choose to put as columns of your time domain template matrix makes a world of a difference. And this visualization on the right shows some of the columns that we have included in the template matrix F, where I have taken time domain templates and I've unrolled them into a two-dimensional maps where time runs in the horizontal axis, along the horizontal axis, and the phase of the instrument runs, the spin phase of the spacecraft runs along the vertical axis. Really cool way of visualizing time domain data that spans 2.5 years for this one HFI detector. So these columns include all of the known systematics. We have the noise offsets, gain fluctuations, and additional templates to capture a whole hierarchy of HFI analog to digital conversion nonlinearities. One of the columns is dedicated for the orbital dipole, which we know to be there and which changes as the spacecraft travels around the sun. So it's a time domain template. You cannot collapse it over the entire span of Planck observations onto a stationary sky map. But when you include it as a separate template in the time domain template matrix, it means that you're measuring the absolute calibration of your instrument as a part of the map making procedure, which is a really cool addition to this thing. There are the zodiacal light templates there that are very relevant for some of the higher HFI frequencies. And then there are these transfer function residuals. But probably the most important piece in this matrix is actually here in POL 30 gigahertz, 217 gigahertz, and 353 gigahertz. This is the parametrized sky model that is fitted as a part of the entire data reduction process. And by adding these polarization templates, we break the degeneracies that would otherwise exist in accommodating for polarization in the stationary sky map here. And that makes a world of a difference, as we'll see in just a second. There is a penalty to pay for adding those polarization templates into this F matrix here, instead of keeping them as degrees of freedom here in the sky map, and that is this large scale polarization bias that we accrue. And this is something that you need to be sentient if you're taking the NPIPE maps to analyze polarization at scales of L less than 20. It's a very stable suppression of large-scale power that comes from assuming that you can decompose the sky polarization degrees of freedom into those very limited templates that are being provided. But when you do that, you have to run a bunch of Monte Carlos so that you can measure just how much your processing is suppressing the input CMB power. And these transfer functions plotted here demonstrate that for all of the HFI frequencies and commander CMB maps that derive most of their statistical power from the HFI frequencies, the transfer function is essentially identical because the degrees of freedom being fitted at all of these different frequencies are the same. For the two LFI frequencies that we measure the transfer function for, we measure a very different and much less suppressive bias due to there being fewer degrees of freedom to fit and to use as a filter. And that transfer function is also very stable with respect to sky area that you consider. The only measurable differences really occur when you limit your focus on just 10 or 20% of the sky. This is where you start to see differences and deviations from the more or less canonical transfer function that we measure. And while these transfer functions may look a little daunting, the effect is really limited to a handful of multipoles. And as a visualization here, I've simulated a CMBE mode map here on the first column. Q and U maps are both smoothed to 3 degrees so that you don't see the small scale structure, but rather the large scales that are more affected by the transfer function. And then in the center column, I'm showing those same maps, but with the signal suppression that comes from the application of this polarization prior in the calibration process. And finally, I'm showing the difference, the amount of lost power due to the transfer function here on the right. Obviously not ideal. We would all like to deal with unbiased data sets, but sometimes it's worthwhile to limit your exposure to the modes in the data that you're just not sensitive for, especially when there is a well-characterized transfer function that allows you to correct for your power spectra for those uncertainties. Going forward, I put together here a slide that really really shows the advantages of these numerous differences between public release 3 and the NPIPE processing. What we have here is a null map comparison, both for public release 3 and for NPIPE. I'm taking the HFI detector set maps and taking the difference between the two. And in the difference, I cancel the sky signal, leaving only noise and systematics. Less is better. If we got a null map, we'd be very happy, but of course the instrument is noisy. So even in the absence of all systematic effects, you would expect to see detector noise in these maps. In the Planck case, there are certainly systematics as well that survive that differencing and the calibration procedure to make these maps. So in here, we can compare the blue power spectrum of the null map to the orange power spectrum of the NPIPE map, and observe a suppression of both large scale and small scale noise and systematics in these maps across all HFI frequencies that I'm plotting here and across all angular scales that I'm comparing here. And these log scale plots may be difficult to read, so I've taken the liberty of computing the ratio of these blue and orange curves and plotted them here on the right. And let's just focus on this column here on the right for a little bit. This is the ratio of the noise bias between the 2018 release and the NPIPE release in 2020. And at the very highest angular scales, smallest angular scales, highest multipoles, we measure about a 10% improvement at 100 gigahertz. That bit is really easy to explain. That's what you get from just adding that repointing maneuver data and survey 9. Adding integration time will drop your noise levels. anything beyond the top of this gray zone here is an improvement over that initial 10% advantage that you get from adding integration time. And as you approach the larger angular scales, that advantage becomes an order of magnitude at the largest multiples. And this is from transfer function corrected NPIPE data. So this is already paying the penalty of amplifying your large scales by deconvolving that transfer function that I just discussed. And there's a different reason for different angular ranges in these sparse spectra comparisons that that contributes. The degree scales are mostly are very much dominated by the application of that short baseline Destriper. And the very largest angular scales benefit most from the application of the polarization prior and then in the calibration process. So there are several different reasons why we find these very, very favorable CL ratios, noise bias ratios. But all in all, they tell a very easy to accept story of there being an improvement across all angular scales and all frequencies. From the tweaks that we've done in the pipeline and the act of combining the best parts of the LFI and HFI pipelines into a unified Planck data processing pipeline. Sharing has been paused. Sorry, that was me. Okay.
Reijo, why don't you serve as your own chair and solicit questions?
I'm going to, but in just a second, because I have 2 more slides to go through. First of all, this slide here is just to show that I've only shown you just a little bit of the almost 100 pages of the NPIPE paper, and you should go in there and judge for yourself if I've left out anything significant, because there are a lot of things, not a lot of comparisons, a lot of results that there simply isn't time to cover in a short talk. And then this concluding slide here just points out that the data are available. Please go and explore. There's a lot to do, a lot to find out. And as a final conclusion, I'll just reiterate some of the points that I've already gone over, but just to act as a cap, first of all, there are significant improvements over some earlier Planck data releases in the NPIPE release. Much of these advantages come from treating the Planck data set as a whole rather than doing individual frequency or individual instrument analysis. Despite all of these successes, the transfer function issue is something that you'll need to be cognizant of, and that comes from the crude sky model that NPIPE implements. And that sort of segues into BeyondPlanck in a very efficient manner, because the natural evolution of this process really is to solve for the sky model in a uniform setting, as is done in BeyondPlanck. There's lots to explore in NPIPE. Charles already mentioned this recent scalar to tensor ratio paper, and NPIPE release is really the first Planck data release where we didn't chew on everything, every scientific aspect of the data set before we released it. So it's out in the wild, it's public, and while we're looking and analyzing the data ourselves, anyone can do it. And there are certainly gold nuggets in there, if though there could be a few hidden rocks as well under the water. So that's all I had.